So in the last video we learned this kind of this strange idea that we called implicit differentiation, and it's where we just thought of y as a function of x. Even though we didn't know the function, we said implicitly we're just going to think of y as a function of x, and then we use the chain rule to actually differentiate an expression with x's and y's in it. Okay, so let me show you how this is used. I'll give you an example here. So we have a unit circle, and the equation of the unit circle here is x squared plus y squared is equal to 1. And what I want to do is I want to find the slope of the tangent lines of these points. So like this, there's a point here, there's a point here, and I want to find the slope of these two tangent lines on these 2 points. Okay? Now there's 2 ways to do this. One way you already know how to do, and so let me do it that way first, and then I'll show you how you can use implicit differentiation. So the way that I'm thinking is you can write this, you can write y as a function of x, but what you're going to do is, in order to get the full circle, you'll have one function will be the top semicircle, the other function will be the bottom semicircle. So what I'm going to do here is I'm going to solve for y. So I get like y squared is equal to 1 minus x squared. Okay, and then I'm going to take plus or minus the square root of both sides, right? And so I'm going to get y is equal to plus or minus the square root of 1 minus x squared. So here we have 2 functions. So you have like y is equal to the square root of 1 minus x squared, and y is equal to the square root of the opposite of the square root of 1 minus x squared. Okay, I'm going to erase this, and I'm going to just write them like this because I want to make it more clear. Okay, so these 2 functions together form the entire graph here of this. Okay, and this is the top semicircle. So if I wanted to find the slope of this, so now I can ignore this, and then I have this function, and then I can find the slope of this tangent line using this function. Okay, so I'm going to do that first, and then I'll find the slope of this tangent line using this function. Okay, so the first one, this one here, so I'm going to do dy dx, and I'm going to take the derivative of this. So that'll be bringing down the 1/2, and I have 1 minus x squared to the negative 1/2, and then I got to take times the derivative of the inside function, which is negative 2x. Okay, so I get all of this, and then I could simplify this into these negative 2 and the 2 cancel out to negative 1. So I get negative x over the square root of 1 minus x squared. So I would get that. And now if I want to find the derivative here, or the slope of the tangent line at this point, then I'm going to plug in 1/2 into this derivative. So I would have dy dx when x is equal to 1/2. And so now I can plug in 1/2 here. I'd get the opposite of 1/2 divided by, and then I put 1/2 down here, square root of 1 minus 1/2 quantity squared. Okay, and so this would be the 1/2 would be 1/4, so I'd get 3/4 here, so I'd have like negative 1/2 over the square root of 3/4, and so I could rewrite this as negative 1/2 over the square root of 3 over 2, and then I could maybe I'll write it down here. Then I could invert this and multiply. I'd get like negative 1 over the square root of 3, and it looks like this is actually the negative square root of 3 over 3 if I rationalize the denominator. So that would be the slope of this tangent line. It is negative, and that's actually the slope of the tangent line there. Okay? So now what about this one? Well, I can do the same thing here, but I'm going to use this function down here. So let's try that. So dy dx, right? I can bring down the 1/2. I'd have a negative already. Then I'd have 1 minus x squared to the negative 1/2. And this would be minus 2x. And now the negatives cancel out, the 2's cancel out, and I'm just going to get x over the square root of 1 minus x squared. And now I would get dy dx for x equals 1/2. And now I could plug it into here. So if I do that, I'm going to get 1/2 on top, and then the square root of 1 minus 1/2 squared. Now this thing ends up being the square root of 3 over 2, right? So I have 1/2 over the square root of 3 over 2. Then I invert and multiply. I get a positive 1 over the square root of 3, which is square root of 3 over 3. So it's the same number, but now it's a positive slope. Okay? So that would be the slope of the two tangent lines here. Okay, well, this is what we've already done, okay? But now let me show you how you could use implicit differentiation to do this, okay? Here's how it works. So we're going to have the unit circle, right? And we want to find the slope at those 2 points. So maybe I'll draw my unit circle here. And there's like this is like 1/2. So this is like 1/2 square root of 3 over 2. And then down here is 1/2 negative square root of 3 over 2. And I want to find the slope of these two tangent lines. Okay? So what I'm going to do is I'm going to use implicit differentiation now. And here's how it works. What I'm going to do is if I have an equation involving x's and y's, like this, then I'm going to take the derivative of both sides. So this would be like this. So the derivative of this with respect to x would be 2x plus 2y dy dx. Okay, this is implicit differentiation. So this with respect to x is just 2x. This one, I treat the something squared with y inside. So I do the derivative of the outside function evaluated at y times the derivative of the inside function, which is just dy dx. Okay, so that's this side. Now if I take the derivative of 1 with respect to x, I would get just 0. Okay, so now I get an expression that involves dy dx and x and y. So now what I'm going to do is I'm going to solve this expression for dy dx. So I'll move this to the other side. 2y dy dx is equal to negative 2x. Okay, and then I divide both sides by 2y, and I get dy dx is equal to negative 2x over 2y. And it looks like those 2's cancel out, so then I get dy dx is just equal to negative x over y. And so this is my dy dx. And it is now an expression involving x and y. So if I want to find the derivative at this point, I could write it like this. dy dx at the point 1/2 square root of 3 over 2. Okay, so now what I'm going to do is I'm going to put this into this expression. So if I do this, I'm going to get opposite of 1/2 over, and then the y would be square root of 3 over 2. And then if I invert and multiply, this would get me negative 1 over the square root of 3, which is negative square root of 3 over 3. And if you look here, that's this tangent line for the top semicircle, indeed, I got negative square root of 3 over 3. Same thing. Okay, so now we can do the bottom one using the same equation. It's just now a different ordered pair. dy dx for the ordered pair 1/2 negative square root of 3 over 2. So plugging it into here, I get the opposite of 1/2 over, and then this would be the opposite of the square root of 3 over 2. So the two negatives cancel out. I would get 1 over the square root of 3, which is just the square root of 3 over 3. And that's this bottom semicircle. It's that tangent line. And there it is, positive square root of 3 over 3. Okay? And so this implicit differentiation, you get an expression in terms of x and y for any point on the unit circle, and you can just take that point, put it in, and find out what the slope of the tangent line is going to be at that point. And so that is the idea of implicit differentiation. It allows you to find slopes of tangent lines for graphs that are not necessarily functions. Okay? Now with this circle, that's a fairly simple relation. That's not a function. And you can split it up into two semicircles, and you can use the old technique. So now in the next video, we're going to look at a function that we're not going to just easily be able to solve for y in terms of x. We won't have that ability. It won't solve nicely like that. And so really implicit differentiation is the only way that we can find the slope of the tangent line in that case.